roughly 100 kilometers south of Cairo, on the western edge of the Nile Valley, where the desert meets the cultivated fields of the Fayoum, there stands a shape that does not belong. It is not a pyramid, not in any way that the word suggests. It is a tower. A steep-sided, flat-topped tower of rough limestone that rises abruptly from a mountain of rubble, like the core of some vast structure that has been stripped of everything around it. The shape is wrong. The proportions are wrong. The context is wrong. A lonely tower standing in the desert, surrounded by a sloping mound of debris that extends outward for hundreds of meters in every direction, covering the desert floor like the skirts of a collapsed tent. This is the Pyramid of Meidum, or rather, this is what remains of it. Because the Pyramid of Meidum was once a complete structure, first a 7-step pyramid, then an 8-step pyramid, and finally, in the most ambitious and the most disastrous phase of its construction, an attempt at a true pyramid with smooth, unbroken sides, rising from base to apex at a consistent angle. The attempt failed. The smooth outer casing, the limestone blocks that were applied to the outside of the stepped core to create the appearance of a true pyramid, collapsed. The collapse was catastrophic. The casing blocks slid away from the core in an avalanche of stone that cascaded down the sides of the pyramid and spread across the desert floor in the vast apron of rubble that surrounds the structure today. The core was left standing, stripped, exposed, diminished, a monument not to the pharaoh's eternal glory, but to the most spectacular structural failure in the history of ancient architecture. The Pyramid of Meidum is the building that fell apart. It is the first great failure of the Egyptian pyramid building tradition. The structure that proved, through its dramatic and destructive collapse, that the transition from the step pyramid to the true pyramid was not a simple cosmetic change, but a fundamental structural transformation that required engineering knowledge the builders did not yet possess. The collapse destroyed the building, but it created something more valuable than any building. Knowledge. The knowledge of what went wrong. The knowledge of why the casing failed. The knowledge of what would need to be different if the next attempt were to succeed. The Meidum collapse was the tuition, the price that the Egyptian building tradition paid for the education that would eventually produce the bent pyramid, the red pyramid, and the Great Pyramid of Giza. By the end of tonight, you're going to understand the story of the pyramid that collapsed, the pyramid that taught the greatest builders of the ancient world their most painful and their most productive lesson. The story of Meidum is not a story of defeat. It is the opening chapter of the most important engineering education in human history. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it genuinely helps this channel reach more curious minds like yours. The numbers tell part of the story. The original pyramid, when the conversion to a true pyramid was complete or nearly complete, stood roughly 92 meters tall, with a base measuring roughly 144 meters on each side. The structure contained hundreds of thousands of cubic meters of stone, quarried, shaped, transported, and placed by a workforce whose skill and dedication were beyond question. The scale of the investment, in labor, in materials, in administrative capacity, in the economic output of the state, was enormous by the standards of the early 4th dynasty, and the loss of that investment when the casing collapsed was one of the most devastating economic events in the history of the Old Kingdom. Today, the tower that remains stands roughly 65 meters above the surrounding rubble, a dramatic reduction from the original height that reflects the loss of the outer layers of the stepped core as well as the complete loss of the smooth casing. The rubble apron that surrounds the base extends outward for hundreds of meters, a vast field of broken limestone blocks, limestone fragments, and sand that covers the desert surface and that conceals, beneath its surface, the remains of the casing that was supposed to make the Meidum Pyramid the first true pyramid in history. The apron is the tomb of the ambition, the physical remains of the hope that was invested in the conversion, and that was destroyed when the conversion failed. The Meidum Pyramid is rarely visited by tourists. It is far from Cairo, far from the popular monuments of Giza, and far from the tourist infrastructure that makes the more famous sites accessible and comfortable. The isolation has preserved the site from the commercialization that has transformed Giza into a tourist spectacle, but it has also contributed to the Meidum Pyramid's obscurity, to the public's ignorance of a structure that is, in many ways, more important to the history of Egyptian architecture than the Great Pyramid itself. The Great Pyramid is the culmination of the tradition. The Meidum Pyramid is the beginning, the painful, destructive, essential beginning, without which the culmination would never have been reached. Now, let's begin. The Pyramid of Meidum occupies a unique position in the history of Egyptian architecture. It stands at the boundary between the old tradition and the new, between the stepped pyramids of the Third Dynasty and the true pyramids of the Fourth, between the world that Imhotep created and the world that Sneferu would transform. The pyramid was begun during the Third Dynasty, probably by Huni, the last pharaoh of that dynasty, and was completed and transformed during the early Fourth Dynasty by Sneferu, who inherited the structure from his predecessor, and who would make the fateful decision to convert it from a step pyramid to a true pyramid. The conversion was the turning point. The moment at which the ambition to build a true pyramid first encountered the reality of what that ambition required, and the moment at which that reality proved to be more demanding than anyone had anticipated. The original design of the Meidum Pyramid was conservative, a step pyramid in the tradition of Djoser's step pyramid at Saqqara, built roughly a century earlier. The pyramid was constructed in stages, first as a 7-step structure, then expanded to an 8-step structure, each step consisting of a layer of limestone blocks built at an inward lean against a central core. The stepped profile was familiar. It followed the established pattern of the step pyramid, a pattern that the builders understood and that they had the technical knowledge to execute successfully. The step pyramid form was stable. The inward lean of the courses directed the weight toward the center of the structure, and the stepped profile distributed the weight across a series of progressively smaller platforms that rested securely on the platforms below. The site of Meidum was located far to the south of the earlier pyramid sites at Saqqara and Dahshur, roughly 100 kilometers south of Memphis, the capital of the Old Kingdom state. The location was unusual. It was distant from the capital, distant from the established cemetery at Saqqara, and distant from the administrative and logistical infrastructure that supported the pyramid building program. The reason for the choice of Meidum as a construction site is not entirely clear. It may have been related to the political geography of the late Third Dynasty, to the location of royal estates or administrative centers in the Fayum region, or to the geological characteristics of the site, which offered a limestone plateau suitable for pyramid construction. The construction of the step pyramid phases proceeded without apparent difficulty. The builders used the established techniques of stone quarrying, transport, and placement that had been developed over the preceding century, and the stepped structure rose from the desert floor in a manner that was consistent with the builders' experience and their expectations. The 7-step phase was completed successfully. The 8-step expansion was completed successfully. The step pyramid of Meidum was, by all indications, a structurally sound and architecturally conventional structure that embodied the state-of-the-art in Old Kingdom pyramid construction, and then Sneferu decided to change it. The decision to convert the step pyramid to a true pyramid was revolutionary. It represented the first attempt in Egyptian history to create a structure with smooth, unbroken sides rising from base to apex at a consistent angle. The decision may have been motivated by religious developments, changes in the solar theology that emphasized the pyramid as a solar symbol, a representation of the sun's rays descending to earth, a form that required smooth sides rather than stepped ones to convey its symbolic meaning. The decision may also have been motivated by aesthetic ambition, the desire to create a more visually impressive structure, a monument that would dominate the landscape more completely than a stepped structure could. Whatever the motivation, the decision was made, and the consequences would transform the history of Egyptian architecture. The geological characteristics of the Meidum site played a role in both the construction and the collapse of the pyramid. The site was located on a limestone plateau that provided both the foundation for the pyramid and the quarries from which the core blocks were extracted. The limestone at Meidum was of variable quality. Some layers were hard and dense, suitable for structural use, while others were softer and more prone to fracture, suitable only for fill material. The builders selected their stone with care, choosing the harder layers for the structural elements, and using the softer material for the interior fill that constituted the bulk of the pyramid's volume. The selection process demonstrated the builder's understanding of stone quality, an understanding that was essential for the construction of a structurally sound building, but that was not, by itself, sufficient to prevent the collapse of the casing. The internal structure of the step pyramid phases, the 7-step and 8-step configurations that preceded the true pyramid conversion, was built using the established technique of inward-leaning courses. Each layer of the stepped structure was built with the courses tilting slightly inward toward the center of the pyramid, creating a stable configuration in which the weight of each layer was directed toward the core rather than toward the edges. The inward-leaning technique was the standard method for step pyramid construction. It had been used at the step pyramid of Saqqara a century earlier, and it was well understood by the builders who worked at Meidum. The technique was effective for step pyramids. The inward lean created a self-supporting structure that was stable against the forces of gravity, and that could withstand the accumulated stresses of centuries without significant deformation. The problem arose when the builders attempted to convert the stepped structure to a true pyramid by adding a smooth casing to the outside of the steps. The casing was not built with the same inward-leaning technique that characterized the stepped core. It was built in layers that were oriented parallel to the sloping surface of the pyramid rather than leaning inward toward the center. The different orientation of the casing courses meant that the casing was not structurally integrated with the core. The two elements were, in effect, independent structures, resting against each other but not locked together, and subject to different forces that could cause them to behave differently under load. The forces acting on the casing were primarily gravitational, the weight of each casing block pulling it downward along the sloping surface of the pyramid. The gravitational force had two components: a component perpendicular to the surface, which pressed the block against the underlying step, and a component parallel to the surface, which pulled the block downward along the slope. The perpendicular component created friction that resisted the downward pull, but the parallel component worked to overcome the friction, pulling the block down the slope with a force that was proportional to the weight of the block and to the sine of the slope angle. As the pyramid rose and the weight of the overlying blocks increased, the parallel force on the lower blocks increased as well, eventually exceeding the friction that held them in place and initiating the sliding that led to the collapse. The analysis of the forces, expressed here in modern terms but understood by the builders only intuitively through the evidence of the collapse itself, reveals the fundamental engineering problem that the Meidum conversion created. The casing was held in place by friction alone, and friction, while adequate for small loads and gentle slopes, was not adequate for the enormous loads and the relatively steep slope of a pyramid the size of Meidum. The solution, which the builders would develop over the subsequent decades at the Bent Pyramid and the Red Pyramid, involved changing the orientation of the casing courses from slope parallel to horizontal, a change that eliminated the sliding force entirely and that held the casing in place through the compressive force of the overlying blocks rather than through friction alone. The religious significance of the Meidum Pyramid. The spiritual and theological context in which the construction was undertaken provides essential background for understanding why the builders attempted the conversion despite the engineering risks that it entailed. The pharaoh's tomb was not merely a building. It was a sacred instrument, a structure that was designed to facilitate the pharaoh's transformation from mortal king to immortal god. The form of the tomb was not arbitrary. It was determined by the religious beliefs of the period, and changes in those beliefs could drive changes in the form of the tomb. The transition from the step pyramid to the true pyramid was, at least in part, a religious transition. a change in the symbolic vocabulary of royal funerary architecture that reflected changes in the solar theology that dominated the religious thought of the late 3rd and early 4th dynasties. The solar theology associated the pyramid with the sun. The pyramid's form was interpreted as a representation of the sun's rays descending to Earth, a cosmic connection between the heavens and the terrestrial world. The stepped pyramid form, with its visible steps, did not convey this symbolism as effectively as the smooth-sided true pyramid form, which created a continuous surface that could be interpreted as a solidified sunbeam. The desire to create a form that more effectively conveyed the solar symbolism may have been one of the motivations for the conversion, a religious imperative that drove the builders to attempt something that their engineering knowledge was not yet sufficient to achieve. The question of attribution, whether the Meidum Pyramid was built by Huni or by Sneferu, is one that has generated considerable scholarly debate, and that has implications for understanding the political and dynastic context of the pyramid's construction. The traditional attribution to Huni is based primarily on the fact that Huni was the last pharaoh of the 3rd dynasty, and that the Meidum Pyramid's initial step pyramid phases are consistent with the architectural conventions of the 3rd dynasty. The attribution to Sneferu is based on the evidence of graffiti found in the mortuary temple and in some of the surrounding mastaba tombs, graffiti that mentions Sneferu's name, and that suggests his involvement in the construction or the completion of the complex. The most likely scenario, accepted by most modern scholars, is that the pyramid was begun by Huni as a step pyramid and was completed and converted to a true pyramid by Sneferu. The scenario makes sense both architecturally and politically. The step pyramid phases are consistent with 3rd dynasty practice, while the true pyramid conversion is consistent with the ambitious building program that characterized Sneferu's reign. The conversion would have been one of the first projects of Sneferu's reign, an early expression of the ambition that would drive the construction of the bent pyramid and the red pyramid at Dashur, and that would culminate in the following generation in the Great Pyramid of Giza. The workforce that built the Meidum Pyramid, both the step pyramid phases and the true pyramid conversion, was organized along the same lines as the workforces that built the other Old Kingdom pyramids. The workers were organized into teams and divisions, hierarchical groups that were supervised by foremen and administrators, and that were supplied by a logistics system, providing tools, materials, food, and water. The workers included quarrymen who extracted the limestone blocks from the plateau quarries, transport teams who moved the blocks from the quarry to the construction site on wooden sledges, masons who cut and fitted the blocks to their final dimensions, and labourers who performed the heavy lifting and hauling that the construction required. The provisioning of the workforce was a significant logistical undertaking. The workers needed to be fed, housed, and supplied with tools throughout the construction period. The food supply came from the royal estates and from the agricultural surplus of the surrounding region. Bread, beer, meat, and vegetables that were transported to the construction site and distributed to the workers according to their rank and their assignment. The housing for the workers has not been identified at Meidum. The workers' settlement has not been located and excavated, and the evidence for the daily life of the construction workforce is limited to what can be inferred from the evidence at other pyramid sites, particularly the well-documented workers' village at Giza. The copper supply was essential for the quarrying operations. Copper chisels were the primary cutting tools, and they dulled rapidly on limestone, requiring constant resharpening at forges maintained at the construction site. The copper came from the mines of Sinai, transported across the desert and the Gulf of Suez to the Nile Valley, and then to the construction site. The timber supply was equally essential. Wood for sledges, levers, scaffolding, and rollers was needed in large quantities, and the best timber came from the cedar forests of Lebanon, transported by sea and river to the construction site. The management of these supply chains required administrative sophistication that the Egyptian state had been developing since the earliest dynasties, and that reached its peak during the 4th Dynasty building program. The transition from the third to the fourth dynasty also involved changes in the political structure of the Egyptian state, changes that gave the pharaoh greater control over the resources of the kingdom, and that made possible the unprecedented scale of the fourth dynasty building program. The third dynasty state had been a relatively decentralized system. The provincial governors had exercised considerable autonomy, and the pharaoh's control over the resources of the provinces had been limited by the need to negotiate and to accommodate the interests of the local elites. The fourth dynasty state was more centralized. The pharaoh exercised direct control over the provincial administrations. The tax revenues flowed more directly to the central treasury, and the state's capacity to mobilize resources for monumental construction was correspondingly greater. The centralization of the fourth dynasty state was both a political achievement and an administrative one. It required not merely the assertion of royal authority, but the development of institutional mechanisms for collecting revenues, managing labor, tracking resources, and coordinating the many parallel activities that a centralized state required. The mechanisms were the same mechanisms that would be needed for pyramid construction. The skills of resource management, labor coordination, supply chain logistics, and quality control that the state bureaucracy developed for the purposes of governance were directly transferable to the purposes of construction. The pyramid building program was, in this sense, an extension of the state building program, a project that employed the same institutional capacities and the same administrative skills that the centralized state had developed for its own operation. The Meidum Pyramid was one of the first beneficiaries of the increased centralization. The resources that flowed to the construction site were drawn from a wider base than had been available to previous pharaohs, and the administrative apparatus that managed the construction was more sophisticated and more efficient than any that had been deployed on a building project before. The increased resources and the improved administration made the Meidum Pyramid possible. They provided the labor, the materials, and the organizational capacity that the construction required. But they could not prevent the collapse, because the collapse was caused by a gap in knowledge, not by a gap in resources, and no amount of wealth or organizational sophistication could compensate for the absence of the engineering understanding that the true pyramid form required. The conversion involved filling in the steps of the existing pyramid with a casing of smooth limestone blocks that were applied to the outside of the stepped core to create a continuous surface that rose from the base to the apex at a uniform angle of approximately 51 degrees. The conversion was, in concept, straightforward. The steps were filled with packing blocks, and the exterior was finished with a smooth casing of fine limestone that created the appearance of a true pyramid. The concept was simple. The execution was catastrophic. The fundamental problem was one of bonding, the connection between the new casing and the existing stepped core. The casing blocks were not structurally integrated with the core. They were applied to the outside of the steps, resting on the surfaces of the existing structure, rather than being built as an integral part of a unified whole. The casing was, in structural terms, a veneer, a thin layer of stone applied to the outside of a much larger structure without the kind of deep, interlocking connection that would have been needed to prevent the casing from separating from the core under the influence of gravity. The transition from Third Dynasty to Fourth Dynasty also involved changes in the political structure that gave the pharaoh greater control over the resources of the kingdom. The Fourth Dynasty state was more centralized. The pharaoh exercised direct control over provincial administrations. Tax revenues flowed more directly to the central treasury, and the state's capacity to mobilize resources for monumental construction was correspondingly greater. The centralization was both a political achievement and an administrative one, requiring institutional mechanisms for collecting revenues, managing labor, and coordinating activities that were directly transferable to pyramid construction. The workforce at Meidum was organized into teams and divisions supervised by foremen and administrators, and supplied by a logistics system providing tools, materials, food, and water. The workers included quarrymen extracting limestone from the plateau quarries, transport teams moving blocks on wooden sledges, masons cutting and fitting blocks, and labourers performing heavy hauling. The provisioning required bread, beer, meat and vegetables transported from royal estates and the surrounding region. The copper supply from Sinai mines was essential for quarrying. Copper chisels dulled rapidly and required constant resharpening. Timber from Lebanese cedar forests was needed for sledges, levers, and scaffolding. Managing these supply chains required administrative sophistication that the Egyptian state had been developing since the earliest dynasties, and that reached its peak during the Fourth Dynasty building program. Sneferu's decision to complete and convert the Meidum pyramid was among his first acts as pharaoh, reflecting his character as a ruler remembered by later generations as benevolent and popular, willing to invest state resources in ambitious projects. The later Egyptian tradition remembered Sneferu fondly, one of the few pharaohs consistently portrayed positively, a reputation that may reflect the lasting impact of his building program. The economic foundations for supporting the Meidum construction were the same that would support Sneferu's entire building program. The agricultural surplus of the Nile Valley, the labour reserves of the Corvi system, and the administrative apparatus that coordinated resources. The wealth and organisational capacity of the early Fourth Dynasty state made the ambitious building program possible, but wealth and organisation are not substitutes for knowledge, and the knowledge that the true pyramid required had not yet been generated. The physical characteristics of the limestone at Meidum, a nummulitic limestone composed of fossilized marine shells, have been studied by geologists who found the stone relatively soft compared to the denser limestone at Giza. The softness may have contributed to the collapse. The relatively weak stone may have been more susceptible to the forces that caused the casing to separate, and weathering over time may have reduced the friction holding blocks in place. The scale of the Meidum pyramid, even in its collapsed state, gives some indication of the ambition and the resources that were invested in the project. The base of the original structure measured roughly 144 meters on each side, a large footprint that required the preparation and leveling of an enormous area of desert surface before the first block could be placed. The height of the completed true pyramid, if the conversion had been successful, would have been roughly 92 meters, making it one of the tallest structures in the world at the time of its construction, and a dramatic visual presence on the landscape of the Western Nile Valley. The volume of stone that the construction consumed was substantial. The stepped core alone contains hundreds of thousands of cubic meters of limestone, and the packing blocks and the casing that were added during the conversion added a further significant volume. The quarrying, the transport, and the placement of this enormous volume of stone required a sustained effort over years, an effort that employed thousands of workers and that consumed a significant share of the state's available labour and economic resources. The investment was enormous, and the loss of that investment when the casing collapsed was one of the most devastating economic setbacks of the early Fourth Dynasty. The mortar used at the Meidum Pyramid, gypsum plaster, produced by heating gypsum rock and grinding the resulting powder, was applied between the blocks to serve as both an adhesive and a levelling agent. The quality and the durability of the mortar were critical factors in the structural performance of the casing. If the mortar weakened over time, the bonds between the blocks would have deteriorated, reducing the friction that held the casing in place and contributing to the conditions that led to the collapse. The role of mortar deterioration in the collapse has been proposed by some scholars as a contributing factor. though the evidence is insufficient to determine whether the mortar failed before the casing or whether the casing failure destroyed the mortar bonds. The surveying and alignment of the Meidum Pyramid, the establishment of the precise square footprint, and the accurate orientation to the cardinal points required the application of geometric and astronomical techniques that the builders had been developing since the construction of the step pyramid. The alignment of the Meidum Pyramid to true north is less precise than the alignment of the later pyramids at Giza, reflecting the continuing refinement of the alignment techniques over the intervening decades. The less precise alignment at Meidum is not evidence of incompetence. It is evidence of the state of the art at the time of the construction, a state that would be progressively improved through the experience gained at each successive pyramid site. The evidence from the construction graffiti at Meidum, while less extensive than the graffiti found at the Red Pyramid, provides some information about the organization and the pace of the construction. The graffiti includes team marks and orientation indicators that were written on the blocks during the quarrying and the placement process. Marks that identify specific teams indicate the intended position of specific blocks and provide evidence for the organizational structure of the workforce. The graffiti is consistent with the marks found at other pyramid sites, suggesting that the organizational practices that would be refined at the later sites were already in use at Meidum, providing a foundation of institutional practice on which the subsequent building program would build. The question of how many construction phases the Meidum Pyramid underwent, how many times the design was changed and the structure was expanded or modified during the construction process has been addressed by scholars through the analysis of the remaining core structure. The analysis reveals at least 3 major phases: the initial 7-step phase, the 8-step expansion, and the true pyramid conversion, and possibly additional minor modifications within each phase. The multiple phases demonstrate that the construction was not a single unified project executed according to a fixed plan. It was an evolving design, modified and expanded as the construction progressed and as the builders' ambitions grew. The evolutionary character of the construction is itself significant. It demonstrates that the Meidum Pyramid, like the step pyramid before it, was a product of a design process that was open to change and that was responsive to the aspirations and the circumstances of its patron. The relationship between the Meidum Pyramid and the nearby Fayum Oasis, the large, fertile depression that lies to the west of the Nile Valley, and that was one of the most productive agricultural regions in ancient Egypt, may have influenced both the choice of the construction site and the provisioning of the workforce. The Fayum provided an additional source of agricultural surplus beyond the Nile Valley itself, a source that was closer to the Meidum site than the estates near Memphis, and that could have supplemented the food supply for the construction workforce. The connection between the pyramid site and the Fayum agriculture is speculative. The evidence does not confirm a direct relationship, but the proximity of the two is suggestive and may help to explain why the Meidum site was chosen despite its distance from the capital. The gravity was relentless. The casing blocks were heavy, each one weighing several tons, and the force of gravity pulled each block downward along the sloping surface of the pyramid. The only force resisting this downward pull was the friction between the casing blocks and the underlying surface, and the friction was not sufficient. The casing blocks began to slide, slowly at first, imperceptibly perhaps, to the builders who were still working on the structure, then faster, as the initial movement disrupted the contact between the blocks and the surface, reducing the friction and accelerating the sliding. And then at some point, the sliding became a cascade, an avalanche of stone that stripped the casing from the core and deposited it in the vast apron of rubble that surrounds the pyramid today. The central mystery of the Meidum Pyramid is not whether the collapse happened. The evidence for the collapse is overwhelming and undeniable. The central mystery is when it happened. A question that has divided Egyptologists for more than a century, and that remains one of the most fiercely debated issues in the study of ancient Egyptian architecture. The question matters because the timing of the collapse determines the lesson that the collapse taught. If the collapse occurred during the construction, while the builders were still working on the conversion, while Sneferu was still alive, while the 4th dynasty building program was still in its early stages, then the collapse would have been a dramatic and immediate lesson, a catastrophe that the builders witnessed firsthand, and that informed their approach to the subsequent constructions at Dashur. If the collapse occurred after the construction was complete, years, decades, or even centuries later, then the collapse would have been a delayed failure, a time bomb that was built into the structure from the beginning, but that did not detonate until long after the builders had moved on to other projects. The evidence for a construction period collapse is suggestive but not conclusive. The most important piece of evidence is the absence of any inscription, any graffiti, any written record that describes the Meidum pyramid as a completed true pyramid. The ancient Egyptians were meticulous record keepers. They documented their construction projects in detail, and the absence of any record describing Meidum as a completed true pyramid has been interpreted by some scholars as evidence that the conversion was never completed, that the collapse occurred before the casing was finished, and that the project was abandoned in the wake of the catastrophe. The evidence for a post-construction collapse is also suggestive but not conclusive. The most important piece of evidence is the character of the rubble apron, the vast mound of debris that surrounds the base of the pyramid. The rubble includes blocks from the upper levels of the casing, blocks that could only have fallen from the pyramid if the casing had been completed to a height sufficient to include them. The presence of upper-level Sikane blocks in the rubble suggests that the casing was completed, or at least substantially completed, before the collapse occurred. The rubble also includes fragments of the fine Tura limestone that was used for the outermost layer of the casing. The finishing layer that would have been applied only after the packing blocks and the structural casing were already in place. The presence of Tura limestone fragments in the rubble suggests that the finishing of the casing was at least partially complete, which in turn suggests that the construction was at an advanced stage when the collapse occurred. The scholarly debate between the early collapse and the late collapse hypotheses has been one of the most productive debates in the study of Egyptian architecture. Not because the debate has been resolved, it has not, but because the debate has forced scholars to examine the structural evidence in unprecedented detail, to develop new methods of analysis, and to refine their understanding of the engineering principles that governed pyramid construction. The debate has also highlighted the difficulty of dating structural events in the archaeological record, the difficulty of determining when a wall fell, when a ceiling cracked, or when a casing slid, using only the physical evidence that the event left behind. Something is wrong with our assumptions when we treat the Meidum collapse as a simple failure of construction technique, as if the builders were incompetent, careless, or ignorant of the forces that their design would create. The builders were not incompetent, they were experienced. They had decades of stone construction experience behind them. They had built the step pyramid phases of the Meidum pyramid successfully, and they understood the basic principles of stone construction well enough to produce structurally sound buildings under normal conditions. The collapse was not the result of incompetence. It was the result of the unprecedented nature of the task. The fact that the conversion from step pyramid to true pyramid was something that had never been attempted before, that the engineering challenges it presented were fundamentally different from the challenges of step pyramid construction, and that the builder's existing knowledge, however extensive, was not sufficient for the new task. And it gets worse, because the Meidum collapse was not merely a failure of technique, it was a failure of concept. The builders treated the conversion as a cosmetic change, as a matter of applying a new surface to an existing structure without fundamentally altering the structural character of the building. They did not recognize that a true pyramid is not a step pyramid with a smooth surface. It is a fundamentally different structural form, subject to different forces, requiring different construction methods, and demanding a different approach to the relationship between the core and the casing. The failure to recognize this distinction was the root cause of the collapse, and the recognition of the distinction, forced by the collapse itself, was the most important lesson that the Meidum disaster produced. The detailed study of the rubble apron that surrounds the Meidum pyramid has provided some of the most important evidence for understanding the mechanics and the timing of the collapse. The rubble has been analysed by geologists, engineers, and archaeologists who have examined the size distribution of the blocks, the composition of the debris, and the spatial pattern of the rubble field to reconstruct the sequence of events that produced the collapse. The analysis has revealed that the rubble is not homogeneous. It consists of multiple layers and multiple types of material that reflect the different stages of the collapse and the different elements of the structure that the collapse destroyed. The outermost layer of the rubble consists primarily of small fragments and sand, material that was produced by the breakage and the erosion of the casing blocks as they slid down the pyramid and across the desert surface. The inner layers of the rubble consist of larger blocks, intact or partially intact casing blocks and packing blocks that fell from the pyramid without breaking, and that came to rest closer to the base of the structure. The size distribution of the blocks in the rubble provides clues about the mechanics of the collapse. The larger blocks tend to be found closer to the base of the pyramid, suggesting that they fell from the lower levels of the casing, where the blocks were larger and heavier, and that they did not travel far from the base before coming to rest. The smaller blocks and fragments tend to be found farther from the base, suggesting that they fell from the upper levels, where the blocks were smaller and lighter, and that they travelled farther from the base before the momentum of the fall was exhausted. The distribution is consistent with a collapse that began at the bottom and propagated upward, a sequence in which the failure of the lower casing blocks removed the support for the upper blocks and caused them to fall in turn. The question of what the Meidum builders knew about the forces that act on a pyramidal structure and what they did not know is central to understanding the nature of the collapse and the nature of the lessons that the collapse produced. The builders knew that stone is heavy. They had decades of experience with the weight and the behavior of limestone blocks, and they understood, in practical terms, how heavy objects behave under the influence of gravity. The builders knew that friction resists sliding. They had experience with the friction between stone surfaces, and they understood, in practical terms, how friction operates to prevent the movement of heavy objects on sloping surfaces. What the builders did not know, what the collapse would teach them, was the quantitative relationship between these forces, the specific conditions under which the friction would be overcome by the gravitational sliding force, and the scale at which the accumulated weight of the overlying blocks would exceed the capacity of the friction to resist the sliding. The knowledge gap was not about principles. The builders understood the principles of weight and friction in practical terms. The knowledge gap was about magnitudes. The builders did not understand the specific magnitudes of the forces that a structure of this size and this angle would create, and they did not appreciate the degree to which the accumulated weight of the upper courses would increase the sliding force on the lower blocks to the point where the friction was overwhelmed. The distinction between knowledge of principles and knowledge of magnitudes is one of the most important lessons of the Meidum collapse, because it explains how competent, experienced builders could produce a catastrophic failure. The builders were not ignorant. They understood the basic principles of stone construction. They understood that heavy blocks on sloping surfaces tend to slide. They understood that friction resists the sliding. What they did not understand was the magnitude, the specific quantitative magnitude of the forces that their structure would create, and the specific quantitative magnitude of the friction that would be needed to resist them. The magnitude was beyond their experience. No previous structure had created forces of this kind at this scale, and the builders had no basis for estimating the magnitudes, except by building the structure and observing the result. The observation of the result, the collapse, provided the magnitude data that the builders had lacked. The collapse demonstrated that the friction on the stepped surfaces was not sufficient to resist the sliding force at the scale of the Meidum pyramid, a demonstration that established, for the first time, a practical upper limit on the forces that could be safely resisted by friction alone. The upper limit was the knowledge, the specific, quantitative, experientially validated knowledge that the builders needed to design structures that would not exceed the limit and that would therefore not collapse. The knowledge was immediately applicable. It could be used to determine the maximum angle, the maximum height, and the maximum weight that a friction-dependent casing could safely support, and it could be used to design alternative casing methods that did not depend on friction alone. The modern understanding of the Meidum collapse has also been informed by experimental archaeology. Attempts to reproduce the conditions of the collapse in controlled settings to test the various hypotheses about the failure mechanisms. The experiments have been limited in scale. It is not feasible to build a full-sized pyramid and observe its collapse, but they have provided useful data about the behavior of limestone blocks on sloping surfaces under various conditions of load, friction, and moisture. The experiments have confirmed that friction on smooth limestone surfaces is insufficient to resist the sliding force at angles comparable to the Meidum pyramid's slope, a confirmation that strongly supports the theoretical analysis and that validates the hypothesis that inadequate friction was a primary factor in the collapse. The experiments have also demonstrated the effectiveness of the countermeasures that the builders developed at the bent pyramid and the red pyramid, particularly the use of horizontal courses rather than slope-parallel courses for the casing blocks. The horizontal courses provide a stable platform for each block, a platform from which the block cannot slide without being lifted over the edge of the block below, a condition that requires a force much greater than the gravitational sliding force that acts on a block resting on a sloping surface. The experimental confirmation of the effectiveness of horizontal courses provides independent validation of the builder's intuitive solution, a solution that was developed through observation and experience rather than through formal analysis, but that was, as the experiments have confirmed, structurally correct. The Meidum pyramid also provides evidence for the development of Egyptian construction safety practices. The measures that the builders took to protect themselves and their workers from the hazards of the construction process. The construction of a pyramid was inherently dangerous. Workers were exposed to the risks of falling blocks, collapsing scaffolding, heat exhaustion, and the physical injuries that result from heavy manual labor. The evidence from other Old Kingdom construction sites, particularly the Workers' Cemetery at Giza, shows that injuries were common and that medical care was available to treat them. The Meidum site has not yielded comparable evidence for safety practices or medical care, but the reasonable inference from the Giza evidence strongly suggests that similar provisions were in place at Meidum, and that the builders took reasonable precautions to protect their workforce from the most serious hazards of the construction process. The question of whether the Meidum collapse itself caused injuries or deaths, whether workers were present on the pyramid when the casing began to slide, and whether any of them were caught in the avalanche of stone that cascaded down the sides, is one that the evidence does not address. The collapse may have occurred gradually enough to allow workers to evacuate the structure before the catastrophic phase of the failure. Or it may have occurred suddenly, without warning, trapping workers on the pyramid and causing casualties that the archaeological record has not preserved. The question is unanswerable, but it adds a human dimension to the engineering story that deserves to be acknowledged, a sobering reminder that the collapse was not merely an abstract structural event, but a human event that affected the lives and possibly the safety of the people who were present when it occurred. The role of the smooth surfaces of the stepped core in the collapse mechanisms deserves particular emphasis, because the surfaces on which the casing blocks rested were the critical interface between the casing and the core, and the properties of these surfaces determined the frictional resistance that held the casing in place. The stepped surfaces were cut during the original step pyramid construction. They were the finished surfaces of the stepped layers, designed to be the final exterior of the pyramid before the true pyramid conversion was conceived. The surfaces were relatively smooth, smoother than the rough quarry faces that would have provided better frictional resistance, and the relative smoothness significantly reduced the friction coefficient between the casing blocks and the core. The reduced friction meant that less gravitational sliding force was needed to initiate the movement of the casing blocks, and the initiation of movement, once it began, was self-reinforcing because the movement disrupted the contact between the surfaces and further reduced the friction, creating a dangerous and self-reinforcing feedback loop that progressively accelerated the sliding until the entire casing had separated from the core. The feedback loop, the self-reinforcing cycle of movement, friction reduction, and accelerated movement, is one of the most important features of the collapse mechanism because it explains the catastrophic character of the failure. A failure that proceeds at a constant rate can often be detected and addressed before it becomes catastrophic. The builders can observe the initial movement, diagnose the cause, and implement countermeasures that arrest the movement before the damage becomes irreparable. A failure that proceeds at an accelerating rate is much more dangerous because the acceleration means that the failure progresses from its initial stages to its catastrophic conclusion more rapidly than the builders can respond, rapidly and completely overwhelming their capacity for observation and intervention, and producing a catastrophe that is complete before any countermeasure can be implemented. The question of whether the collapse was sudden or gradual has also been addressed through the analysis of the rubble. A sudden collapse, a single catastrophic event in which the entire casing failed at once, would produce a rubble field with a relatively uniform distribution because all of the blocks would have fallen at approximately the same time and from approximately the same height. A gradual collapse, a series of partial failures that occurred over a period of time, would produce a rubble field with a more complex distribution because blocks from different levels and different sections of the casing would have fallen at different times and under different conditions. The evidence from the rubble field is more consistent with a gradual collapse than with a sudden one, suggesting that the casing failed in stages, with the initial failure of the lower. The role of water in the collapse has been proposed by some scholars as a contributing factor. Rainfall, which occurs infrequently but occasionally in the desert regions of Egypt, could have infiltrated the joints between the casing blocks and the underlying surface, reducing the friction that held the blocks in place and lubricating the contact surfaces to the point where the sliding force exceeded the frictional resistance. The water hypothesis is plausible. Rainfall events in the Egyptian desert can be intense enough to produce significant runoff, and the infiltration of water into the joints between stone blocks is known to reduce friction substantially. But the hypothesis is difficult to test. The evidence for rainfall events at the specific time of the collapse is not available, and the role of water in the collapse must remain speculative. The engineering analysis of the Meidum collapse has identified several specific failure mechanisms that contributed to the separation of the casing from the core. Mechanisms that, taken together, explain why the casing failed and why the failure was so complete and so catastrophic. The first mechanism was the inadequate bonding between the casing blocks and the surface of the stepped core on which they rested. The casing blocks were laid on the stepped surfaces that were relatively smooth and that offered limited opportunities for mechanical interlocking between the casing and the core. The blocks were held in place primarily by friction, the resistance to sliding that results from the contact between two rough surfaces under compressive load. The friction was initially adequate. When the pyramid was first built, the weight of the overlying blocks pressed the casing blocks against the stepped surface with enough force to resist the sliding component of the gravitational load. But the friction was not permanent. Over time, the contact surfaces may have deteriorated, the mortar that filled the joints may have weakened, and the cumulative effect of thermal expansion and contraction may have loosened the blocks and reduced the frictional resistance to the point where the sliding force exceeded the friction and the movement began. The second mechanism was the orientation of the bedding planes, the surfaces on which the casing blocks rested. The bedding planes of the casing were oriented parallel to the slope of the pyramid, meaning that each block rested on a surface that was tilted at the same angle as the pyramid's face. The tilted bedding plane created a natural sliding surface, a surface along which the block could move under the influence of gravity without having to overcome any obstacle other than friction. If the bedding planes had been horizontal, as they would be at the Red Pyramid and the Great Pyramid, the blocks would have been resting on level surfaces from which they could not slide without being lifted over the edge of the block below. The horizontal orientation would have been inherently more stable, and the failure at Meidum was, in part, a failure to recognize the importance of bedding plane orientation in determining the stability of the casing. The third mechanism was the weight of the overlying blocks. The cumulative load that the lower casing blocks had to bear as the pyramid rose and the number of overlying courses increased. The load on the lowest casing blocks was enormous. Thousands of tons of stone resting on each block, pressing it against the surface below, but also pushing it downward along the slope, with a force that increased as the pyramid grew taller. The increasing load created increasing stress on the lower blocks. Stress that eventually exceeded the capacity of the friction to resist the sliding force, and that initiated the movement that led to the collapse. The fourth mechanism, proposed by some scholars as a contributing factor rather than a primary cause, was the thermal cycling that the pyramid experienced over the centuries. The Egyptian desert is subject to extreme temperature variations, hot during the day and cold at night, and the resulting expansion and contraction of the stone could have gradually loosened the joints between the casing blocks and the underlying surface, reducing the friction and creating gaps through which water could infiltrate and further weaken the connection. The thermal cycling mechanism would have operated slowly, over years or decades rather than days or weeks, and its contribution to the collapse would have been cumulative rather than sudden. The relationship between the Meidum collapse and the development of ancient Egyptian understanding of structural mechanics is one of the most important aspects of the collapse's significance, because the collapse forced the builders to develop an intuitive understanding of forces, loads, and failure mechanisms that would inform every subsequent construction project for the next 2,000 years. Before Meidum, the builders' understanding of structural mechanics was limited to what they had learned from step pyramid construction, a form that was inherently stable and that did not expose the builders to the kinds of forces that true pyramid construction would create. After Meidum, the builders' understanding was expanded, painfully but dramatically, by the experience of watching a structure fail under forces that they had not anticipated and that they now needed to understand if they were to prevent similar failures in the future. The expansion of understanding was not immediate. It occurred over the decades that followed the collapse, as the builders applied their observations of the failure to the design and the construction of subsequent structures. The bent pyramid was the first application, a structure that incorporated countermeasures against the Meidum failure modes, but that encountered new problems that the Meidum experience had not prepared the builders for. The Red Pyramid was the second application, a structure that incorporated the lessons of both the Meidum collapse and the bent pyramid crisis, and that achieved the first successful true pyramid. The Great Pyramid was the final application, a structure that incorporated the accumulated lessons of the entire building program, and that pushed the proven methods to their fullest expression. The progressive expansion of the builder's understanding, from the limited knowledge that preceded the Meidum collapse to the comprehensive understanding that produced the Great Pyramid, is one of the most impressive examples of institutional learning in the ancient world. The expansion was not the work of a single individual or a single generation. It was a collective achievement, the accumulated work of thousands of builders across multiple reigns, each generation building on the knowledge of the previous one and transmitting the expanded understanding to the next generation through the apprenticeship system that was the primary mechanism of knowledge transfer in the ancient world. The relationship between the Meidum collapse and the development of the builders' understanding of structural mechanics forced them to develop intuitive knowledge of forces, loads, and failure mechanisms that would inform every subsequent construction for 2,000 years. Before Meidum, their understanding was limited to step pyramid construction, inherently stable and not exposing them to the forces that true pyramids would create. After Meidum, their understanding was dramatically expanded by the experience of watching a structure fail under unanticipated forces. The expansion occurred progressively over decades. The bent pyramid was the first application, incorporating countermeasures but encountering new problems. The red pyramid was the second, incorporating lessons from both Meidum and the bent pyramid and achieving the first successful true pyramid. The Great Pyramid was the culmination, incorporating accumulated lessons and pushing proven methods to their fullest expression. This progressive expansion was one of the most impressive examples of institutional learning in the ancient world, a collective achievement spanning thousands of builders across multiple reigns, each generation building on the knowledge of the previous one. The identification of these failure mechanisms was one of the most important contributions of the Meidum collapse to the development of the Egyptian building tradition, because each mechanism suggested a specific countermeasure that the builders could apply to prevent similar failures in future constructions. The inadequate bonding suggested the need for better integration between the casing and the core. The slope-parallel bedding planes suggested the need for horizontal courses. The excessive load on the lower blocks suggested the need for a shallower angle that would reduce the sliding force. And the thermal cycling suggested the need for tighter joints and better mortar that would resist the loosening effects of temperature variation. Each countermeasure was applied to varying degrees at the bent pyramid and the red pyramid, and the cumulative effect of all the countermeasures was the structural soundness that characterized the mature pyramid tradition. The modern archaeological investigations of the Meidum Pyramid have employed techniques that were not available to Petrie and his contemporaries. Techniques that have provided new data about the structure and the collapse that supplement the observations of the earlier explorers. The most important of these techniques are the non-invasive survey methods, ground-penetrating radar, seismic tomography, and photogrammetric mapping that allow researchers to study the internal structure of the pyramid and the rubble apron without physically disturbing the ancient fabric. Ground-penetrating radar surveys of the rubble apron have revealed the internal structure of the debris field, the layers and the interfaces that reflect the different stages of the collapse and the different materials that the collapse produced. The radar data have confirmed that the rubble is stratified, that it consists of multiple layers of different character, with the larger blocks closer to the base and the smaller fragments farther away. The stratification is consistent with a collapse that proceeded from bottom to top, a sequence in which the lower casing blocks failed first and the upper blocks fell subsequently, producing a rubble field that reflects the order in which the blocks left the pyramid. Photogrammetric surveys of the remaining core have produced detailed three-dimensional models of the structure. Models that reveal the precise shape of the core, the pattern of the stepped layers, and the condition of the exposed surfaces. The models have confirmed that the core consists of concentric layers of masonry, each layer built at an inward lean against the layer inside it, and that the layers are structurally independent, each one self-supporting and each one capable of standing alone if the layers outside it were removed. The structural independence of the layers is the reason the core has survived. The removal of the casing and the outer layers of the step pyramid did not affect the stability of the inner layers, which continue to stand on their own foundation of inward-leaning courses. The question of whether additional passages or chambers exist within the Meidum pyramid, spaces that were built during the construction but that have not yet been discovered, is one that the non-invasive surveys have addressed but not definitively resolved. The survey data have identified several anomalies within the body of the pyramid, variations in density or reflectivity that may indicate the presence of voids, passages, or other features that are not visible from the exterior. The anomalies have not been verified through excavation, and their nature and significance remain uncertain. The possibility that the Meidum Pyramid contains undiscovered internal features is one of the most intriguing prospects in contemporary Egyptian archaeology, a prospect that combines the scientific rigor of modern survey techniques with the romantic hope that the ancient structure still has secrets to reveal. The debate over the timing of the collapse has been enriched by the modern investigations, but it has not been resolved. The evidence continues to support both the early collapse and the late collapse hypotheses, and the scholarly community remains divided on the question. Some scholars have proposed a compromise position, arguing that the collapse may have occurred in multiple stages, with an initial partial failure during or shortly after the construction period and a more complete collapse at a later date. The compromise position is attractive. It accounts for the evidence that supports both hypotheses without requiring either one to explain all of the data. But the compromise position is also difficult to test. The evidence for a multi-stage collapse is subtle and ambiguous, and the distinction between a single catastrophic event and a series of smaller events is difficult to establish on the basis of the physical evidence alone. But here's what makes this truly terrifying. The Meidum collapse may have been the trigger for the entire revolution in Egyptian construction that followed. If the collapse occurred during or shortly after the construction period, it would have served as a dramatic and unforgettable demonstration of the dangers of the true pyramid form. A demonstration that would have informed every subsequent decision that Sneferu and his builders made at Darsha. The bent pyramid's steep angle, its inward sloping courses, its emergency repairs, all of these features can be understood as responses to the lessons of Meidum, as attempts to avoid the specific failure modes that the Meidum collapse had revealed. The red pyramid's conservative angle, its horizontal courses, its carefully prepared foundation. All of these features can be understood as the mature application of the knowledge that the Meidum and bent pyramid experiences had generated. The Great Pyramid of Giza, the culmination of the tradition, can be understood as the final product of a learning process that began with the catastrophe at Meidum. The Meidum Pyramid story is enriched by the exploration of its specific features. The internal structure, the external form, the surrounding buildings, and the archaeological discoveries that have shaped our understanding of the site and its significance. The first exploration examines the internal structure of the Meidum Pyramid, the passages and chambers that were carved into and beneath the structure during its construction, and that have survived the collapse of the exterior casing. The internal structure of the Meidum Pyramid is relatively simple. A descending passage that enters the pyramid from the north face, passes through the body of the structure, and descends into the bedrock beneath the pyramid to reach a burial chamber that is located at approximately ground level. The descending passage is narrow, roughly 1 meter wide and 1.5 meters high, and it is carefully constructed with walls and ceiling of precisely cut limestone blocks that have maintained their structural integrity despite the collapse of the exterior. The burial chamber is one of the most interesting features of the Meidum Pyramid because it contains one of the earliest examples of a corbelled ceiling in a pyramid context. The ceiling rises in a series of corbelled courses, each course projecting beyond the one below, gradually narrowing the space until it can be spanned by a single block at the top. The corbelling is approximately 7 meters high, impressive for the period and significant as a precursor to the more ambitious corbelled ceilings that would be built in the bent pyramid and the red pyramid. The corbelled ceiling of the Meidum burial chamber survived the collapse of the exterior casing, demonstrating that the internal structure of the pyramid was not affected by the failure of the external structure, and that the two were structurally independent of each other. The second exploration examines the external form of the Meidum pyramid as it exists today, the tower-like core surrounded by the rubble apron, and what this form tells us about the sequence and the mechanics of the collapse. The core that remains standing today is the innermost portion of the original step pyramid, the central tower that was built first and that was surrounded by successively larger and more elaborate, stepped layers as the construction progressed. The core stands roughly 65 meters above the surrounding rubble, a dramatic, isolated structure that bears no resemblance to the smooth-sided pyramid that the builders intended to create. The core is not a single monolithic structure. It consists of multiple concentric layers of masonry, each layer built at an inward lean against the layer inside it, creating a stable, self-supporting structure that has resisted the forces of gravity and erosion for more than 4,600 years. The rubble apron that surrounds the core, the vast mound of debris that extends outward for hundreds of meters in every direction, is the remains of the collapsed casing and the packing blocks that were used to fill in the steps. The rubble is not random. It has a structure that reflects the mechanics of the collapse. The larger blocks are closer to the base of the pyramid. They fell first, from the lower levels, and they did not travel far from the base. The smaller blocks and the fragments are farther from the base. They were carried outward by the momentum of the collapse, sliding and rolling across the desert surface before coming to rest at the outer edge of the rubble field. The distribution of the rubble provides evidence for the sequence of the collapse, suggesting that the failure began at the lower levels of the casing, where the weight of the overlying blocks was greatest, and propagated upward as the removal of the lower blocks destabilized the upper blocks and caused them to slide as well. The third exploration examines the archaeological context of the Meidum Pyramid, the tombs, the temples, and the other structures that surrounded the pyramid and that provide evidence for the social and the religious world in which the pyramid was built. The most famous archaeological discovery at Meidum is not the pyramid itself but a painting, the so-called Meidum geese, a masterpiece of ancient Egyptian painting that was found in the nearby Mastaba tomb of Nefermat and his wife Itet. The painting depicts 6 geese, 3 facing left and 3 facing right, rendered with a naturalism and a precision that is remarkable for any period of ancient art, and that is extraordinary for a painting that is more than 4,600 years old. The Meidum geese have been called the oldest known naturalistic painting in the world, and while the claim is debatable, the painting is unquestionably one of the finest examples of Old Kingdom art and one of the most famous images in the history of Egyptian archaeology. The Mastaba of Nefermat, the tomb that contained the Meidum geese, provides important context for understanding the social world in which the Meidum pyramid was built. Nefermat was a high-ranking official, possibly a son of Sneferu, who served the pharaoh in various administrative and religious capacities. His tomb was located near the pyramid, a placement that reflected his status and his connection to the royal family. The tomb was decorated with painted scenes of daily life, hunting, farming, animal husbandry, and domestic activities that provide one of the most detailed and most vivid pictures of Old Kingdom life that has survived. The fourth exploration examines the engineering lessons of the Meidum collapse, the specific technical insights that the failure produced, and that informed the design of subsequent pyramids. The most important engineering lesson of the Meidum collapse was the lesson about bonding. The lesson that a true pyramid casing cannot simply be applied to the outside of a step structure without a structural connection that is strong enough to resist the gravitational forces that act on the casing. The casing of the Meidum pyramid was not bonded to the stepped core. It rested on the surfaces of the steps, held in place by friction and by the weight of the overlying blocks, but without the interlocking joints, the structural keys, or the deep foundation connections that would have been needed to resist the sliding forces. The collapse demonstrated that friction alone was not sufficient, that the casing needed to be structurally integrated with the core in a way that prevented the casing from sliding, shifting, or separating from the core under the influence of gravity. The lesson about bonding was applied immediately to the design of the bent pyramid, where the casing was more thoroughly integrated with the core than the Meidum casing had been. The bent pyramid's builders used inward-sloping courses for the lower section of the casing, a technique that was intended to direct the weight of each course toward the interior of the pyramid and to prevent the outward sliding that had destroyed the Meidum casing. The technique was partially successful. It prevented the kind of catastrophic casing collapse that had occurred at Meidum, but it created a different set of problems that the builders had not anticipated. The inward sloping courses created potential failure surfaces within the casing, surfaces along which the blocks could shift under lateral pressure, and the failure surfaces contributed to the structural crisis that forced the bent pyramids builders to change the angle partway through the construction. The Meidum pyramid complex included not only the pyramid itself, but a series of associated structures that served the ritual functions of the pharaoh's funerary cult. Structures that provide evidence for the religious practices and the architectural conventions of the late 3rd and early 4th dynasties. The mortuary temple, located on the eastern face of the pyramid, was a small, simple structure that served as the ritual center of the funerary complex. The temple contained 2 tall stelae, uninscribed limestone pillars that flanked the entrance to the temple, and that may have served as markers for the offering rituals that were performed in front of the pyramid. The stelae are significant. They are among the earliest examples of the freestanding stelae that would become a standard feature of Egyptian funerary complexes, and their presence at Meidum demonstrates that the basic elements of the mortuary cult were already in place at this early stage of the pyramid building tradition. The offering table, a stone platform on which food, drink, and other offerings were placed for the spirit of the deceased, was located between the stelae, directly in front of the eastern face of the pyramid. The offering table was the functional center of the cult, the place where the daily offerings were presented, and where the prayers and incantations that sustained the pharaoh's spirit were recited. The simplicity of the offering arrangement at Meidum, a table, 2 stelae, and a small temple, contrasts sharply with the elaborate mortuary temples that would be built at Giza in the following generation, where the temples would include multiple rooms, extensive relief decoration, and complex ritual programs. The contrast reflects the development of the funerary tradition over the intervening decades, a development that was driven by the same process of experimentation and refinement that characterized the development of the pyramid form itself. The causeway that connected the mortuary temple to the valley temple, the covered corridor that served as the ritual pathway between the world of the living and the world of the dead, has been partially traced but not fully excavated. The causeway ran roughly east from the mortuary temple to the edge of the cultivation, where the valley temple was located. The valley temple itself has not been fully excavated. Its remains are buried beneath the alluvial deposits that have accumulated at the edge of the floodplain over the millennia since the complex was built. The incomplete excavation of the valley temple is one of the most significant gaps in our knowledge of the Meidum complex. The valley temple would provide important evidence for the ritual practices and the architectural conventions of the period, and its excavation would be a significant contribution to the study of early 4th dynasty funerary architecture. The mastaba tombs that surround the Meidum pyramid, the tombs of the officials and the family members who served the pharaoh and who were buried near the pyramid as a mark of their status and their connection to the royal family, provide essential context for understanding the social world in which the pyramid was built. The mastabas at Meidum are among the finest examples of early 4th dynasty tomb architecture. They are large, well-constructed structures that were decorated with painted scenes of extraordinary quality and that were equipped with elaborate burial chambers and offering chapels. The mastaba of Rahotep and Nofret, another of the famous tombs at Meidum, contain 2 painted limestone statues that are among the most celebrated works of ancient Egyptian art. The statues depict Rahotep, a prince of the royal family, possibly a son of Sneferu, and his wife Nofret, seated in formal poses with their names and titles inscribed on the backs of their chairs. The statues are remarkable for their naturalistic treatment of the human figure. The lifelike eyes, inlaid with rock crystal and quartz, the carefully modelled features, and the subtle colouring of the skin create an impression of vivid, almost startling presence that has captivated viewers for more than a century since their discovery by Auguste Mariette in 1871. The discovery of the Rahotep and Nofret statues and of the Meidum geese painting in the nearby mastaba of Nefermat demonstrated that the Meidum site was not merely a construction project, but a community of the elite, a gathering of the most powerful and the most talented individuals in the early 4th dynasty state, a microcosm of the court that served the pharaoh in life and that followed him in death. The artistic quality of the tombs reflects the cultural sophistication of the period, a period that was not merely an age of engineering achievement, but an age of artistic achievement as well, a period in which the construction of monumental pyramids was accompanied by the production of paintings, sculptures, and decorative arts of extraordinary quality. The engineering significance of the Meidum Pyramid's corbelled burial chamber extends beyond the specific context of the Meidum site to the broader development of the corbelling technique in Egyptian architecture. The Meidum burial chamber was one of the earliest pyramid contexts in which the corbelling technique was employed, and its success, the chamber survived the collapse of the exterior, demonstrated that the technique was viable for the creation of large internal spaces within stone structures. The demonstration encouraged the builder to employ the technique at the subsequent pyramids at Darsha, where the corbelled ceilings were pushed to more ambitious proportions and where the limitations of the technique were revealed by the structural problems in the bent pyramid's lower chamber. The development of the corbelling technique from the Meidum burial chamber through the bent pyramid's chambers to the red pyramid's chambers and finally to the Great Pyramid's Grand Gallery is one of the most instructive sequences in the history of structural engineering. The sequence shows a clear progression from the modest 7-metre corbelling at Meidum to the ambitious 17-metre corbelling at the bent pyramid, which failed, to the conservative 12 to 15-metre corbelling at the red pyramid, which succeeded, to the magnificent 8.5-metre high Grand Gallery at the Great Pyramid, which succeeded spectacularly. The progression is not linear. It includes the failure at the bent pyramid, which forced a retreat to more conservative proportions, but it is directed, moving consistently toward a better understanding of the technique's capabilities and limitations. The question of whether the Meidum Pyramid's designers intended the corbelled ceiling from the beginning, whether it was part of the original step pyramid design, or whether it was added during the true pyramid conversion, is one that the evidence does not definitively answer. The placement of the burial chamber within the body of the pyramid rather than below it, a placement that is more consistent with the true pyramid tradition than with the step pyramid tradition, suggests that the chamber may have been redesigned or relocated during the conversion process. The possibility that the chamber was redesigned during the conversion adds another dimension to the Meidum story, a dimension in which the conversion affected not only the exterior of the pyramid, but the interior as well, transforming the burial arrangements as well as the architectural form. The Meidum Pyramid's influence on the development of Egyptian passage systems, the corridors that connect the entrance to the burial chamber, is another aspect of its engineering significance that deserves attention. The Meidum passage system is relatively simple. A single descending corridor leading to the burial chamber, but it established the basic pattern that subsequent pyramids would follow: an entrance on the north face, a descending passage aligned approximately with the celestial north, and a burial chamber located at or below the base level of the pyramid. The pattern was modified at subsequent sites. The bent pyramid added a second entrance on the west face. The Great Pyramid added ascending passages and multiple chambers. But the basic elements of the pattern remained consistent, providing a framework of continuity within which individual variations could be accommodated. The relationship between the Meidum pyramid and the nearby smaller pyramid, a small subsidiary structure located to the south of the main pyramid, provides additional evidence for the funerary program that the complex was designed to serve. The subsidiary pyramid is one of the earliest examples of the satellite pyramid form that would become standard at subsequent pyramid sites. A miniature pyramid that served specific ritual functions within the funerary complex. The presence of the subsidiary pyramid at Meidum demonstrates that the basic elements of the mature pyramid complex, the main pyramid, the satellite pyramid, the mortuary temple, the causeway, the valley temple, were already being developed at this early stage of the tradition, even before the true pyramid form had been successfully achieved. The fifth exploration examines the role of the archaeologist Flinders Petrie in the modern understanding of the Meidum pyramid, and the contribution that his meticulous fieldwork made to the study of the site and its significance. William Matthew Flinders Petrie, one of the most important figures in the history of Egyptian archaeology, conducted the first systematic excavation of the Meidum pyramid in 1891. Petrie was a pioneer of scientific archaeology, a practitioner who insisted on meticulous recording, careful measurement, and systematic analysis at a time when many of his contemporaries were content with treasure hunting and casual observation. His work at Meidum established the basic framework of knowledge that all subsequent studies of the site have built upon. The measurements of the pyramid's dimensions, the plans of the internal passages and chambers, the description of the rubble apron, and the analysis of the construction techniques that the builders had used. Petrie's analysis of the Meidum pyramid led him to conclude that the collapse had occurred after the construction was complete, a conclusion that was based on his observation that the rubble apron contained blocks from all levels of the casing, including blocks from the upper levels that could only have been placed if the casing had been completed to a substantial height. Petrie's conclusion was influential. It shaped the scholarly understanding of the Meidum collapse for decades and established the late collapse hypothesis as the dominant interpretation of the evidence. Subsequent scholars have challenged Petrie's conclusion, arguing that the evidence is also consistent with a construction period collapse, and that the debate remains open. But Petrie's contribution to the study of Meidum, his careful fieldwork, his detailed measurements, and his rigorous analysis, remains the foundation on which all subsequent research has been built. The Meidum pyramid's internal passage system, the corridors and chambers that were built into the structure during its construction, provides evidence for the evolving design of Egyptian burial chambers during the transitional period between the 3rd and 4th dynasties. The system is relatively simple: a single descending passage on the north face leading to a burial chamber at approximately ground level, but it includes features that are significant for the development of the tradition. The descending passage is oriented approximately north-south, the standard orientation for pyramid passages, aligned with the celestial north and with the circumpolar stars that the Egyptian religious system associated with the pharaoh's eternal destination. The passage is carefully constructed. Its walls and ceiling are lined with well-cut limestone blocks, and its alignment is straight and precise. The construction quality of the passage demonstrates that the builder's skill in internal construction was not compromised by the structural problems that affected the external casing. The internal passages and chambers were built as integral parts of the stepped core using the established techniques of step pyramid construction, and they survived the collapse of the external casing without significant damage. The burial chamber itself is located at the junction of the descending passage and a short vertical shaft that rises from the passage to the chamber level. The chamber is not large. It measures roughly 5.9 meters long, 2.6 meters wide, and roughly 5 meters high, but it is notable for its corbelled ceiling, one of the earliest examples of the corbelling technique in a pyramid burial chamber. The corbelling rises through 7 courses, each course projecting beyond the one below, gradually narrowing the space to a ceiling that is spanned by a single row of blocks at the top. The corbelled ceiling is significant because it represents an early stage in the development of the technique that would be refined at the bent pyramid and the red pyramid, and that would eventually be superseded by the flat granite ceiling of the Great Pyramid's King's Chamber. The corbelled ceiling of the Meidum burial chamber survived the collapse of the exterior casing, a fact that demonstrates the structural independence of the internal and external elements of the pyramid. The survival confirms that the corbelled ceiling was built as part of the stepped core rather than as part of the casing, and that the forces that destroyed the casing did not affect the internal structure. The survival also provides evidence for the structural soundness of the corbelling technique. The technique worked, even in the earliest pyramid in which it was used, and its success at Meidum encouraged the builders to employ it at the subsequent pyramids at Dacia, where it would be pushed to more ambitious proportions, and where it would encounter the structural problems that the bent pyramid's lower chamber revealed. The question of whether anyone was actually buried in the Meidum pyramid is one that the evidence does not definitively answer. The burial chamber was found empty. No mummy, no sarcophagus, no grave goods were found in the chamber or in the passages leading to it. The emptiness may reflect ancient tomb robbery, the removal of the burial goods by thieves who entered the pyramid through the accessible entrance passage. The emptiness may also reflect the fact that the pyramid was never used for a burial, that the collapse of the casing rendered the pyramid unsuitable as a tomb, and that the pharaoh, whether Huni or Sneferu, was buried elsewhere. If Sneferu was responsible for the conversion, and if the collapse occurred during or shortly after the construction, then Sneferu would have needed an alternative burial place, and the bent pyramid or the red pyramid may have served this purpose. The comparison between the Meidum pyramid and other ancient structural failures provides a broader context for understanding the significance of the collapse and the nature of the engineering lessons it produced. The ancient world contains numerous examples of structural failures: collapsed buildings, failed fortifications, inadequate foundations, but few of these failures have been as consequential as the Meidum collapse, and none have been as directly connected to a subsequent program of engineering development that produced structures of world historical significance. The most instructive comparison is with the Meidum pyramid's own successors, the bent pyramid and the red pyramid at Dashur, which were designed in direct response to the lessons of the Meidum collapse, and which incorporated specific countermeasures that were intended to prevent similar failures. The comparison reveals the progressive refinement of the builder's understanding from the Meidum collapse, which revealed the fundamental problems, through the bent pyramid, which addressed some problems while revealing others, to the red pyramid, which addressed all of the known problems and achieved the first successful true pyramid. The progression is a textbook example of iterative engineering development, a sequence of designs, tests, and revisions that produced, through the accumulation of knowledge from successive failures, a solution that was adequate for the task. The Meidum pyramid also provides an instructive comparison with the engineering failures of other ancient civilizations. Failures that, like the Meidum collapse, revealed the limits of existing knowledge, and that stimulated the development of new techniques and new understanding. The Mesopotamian ziggurats, the stepped temple platforms that were the Mesopotamian equivalents of the Egyptian pyramids, experienced their own structural failures, including settlement, cracking, and partial collapse, that forced the Mesopotamian builders to develop new techniques for foundation preparation, for drainage, and for the structural reinforcement of large mud brick assemblies. The comparison demonstrates that the process of learning from failure was not unique to the Egyptian tradition. It was a universal feature of ancient engineering, a process that operated in every civilization that attempted monumental construction, and that produced, in every case, a body of practical knowledge that was refined through the experience of dealing with structural problems. The artistic treasures discovered in the mastaba tombs surrounding the Meidum Pyramid have made the site one of the most important sources of early 4th Dynasty art, a source that has shaped our understanding of the artistic traditions and the aesthetic values of the period. The paintings in the mastaba of Nefermat, including the famous Meidum geese, demonstrate a mastery of naturalistic representation that is extraordinary for the period, and that suggests the existence of a sophisticated artistic tradition with established conventions for the depiction of the natural world. The statues of Rahatep and Nofret demonstrate a mastery of three-dimensional form that is equally impressive. The modelling of the human figure, the rendering of facial features, and the treatment of clothing and jewellery are all executed with a skill and a sensitivity that place these works among the finest examples of Egyptian sculpture from any period. The development of the Egyptian funerary complex from the simple arrangement at Meidum to the elaborate complexes at Giza reveals a pattern of progressive elaboration that mirrors the pattern of progressive refinement in the pyramid form itself. The Meidum complex was simple, a pyramid, a small mortuary temple with 2 stelae and an offering table, a causeway, and a valley temple. The Giza complexes were elaborate, vast assemblages of temples, causeways, boat pits, subsidiary pyramids, and courtiers' tombs that surrounded the central pyramid and that provided a comprehensive ritual infrastructure for the maintenance of the pharaoh's cult. The elaboration was not merely cosmetic, it reflected a deepening understanding of the ritual requirements of the funerary cult and a growing ambition to provide the deceased pharaoh with a more comprehensive and more effective system of spiritual sustenance. The simple offering arrangement at Meidum, a table and 2 stelae, was adequate for the basic ritual of offering food and drink to the spirit. The elaborate mortuary temples at Giza, with their multiple rooms, their relief decorations, their storage facilities, and their priestly quarters, were designed to support a much more complex ritual program, including daily offerings, festival celebrations, and seasonal ceremonies that marked the passage of the agricultural year. The development from simplicity to elaboration was driven by the slow process of experimentation and learning that drove the development of the pyramid form. The process of trying different arrangements, evaluating their effectiveness, and refining the design on the basis of the evaluation. The Meidum complex was an early experiment, an attempt to establish the basic elements of the funerary complex and to determine the spatial relationships between them. The subsequent complexes at Dashur and Giza were refinements, improvements that built on the Meidum experiment and that progressively developed the complex toward the mature form that it would achieve at the end of the 4th Dynasty. The question of what happened to the Meidum site after the collapse, whether the site was abandoned entirely, or whether it continued to function as a funerary complex, despite the damage to the pyramid, is one that the evidence addresses only partially. The mastaba tombs around the pyramid continued to be used for burials into the later Old Kingdom, suggesting that the site retained some degree of religious significance even after the pyramid's casing had collapsed. The mortuary temple may have continued to function. The simple structure of the temple may have survived the collapse of the casing, and the rituals of the funerary cult may have continued to be performed even if the pyramid itself was no longer in its intended condition. The continued use of the site, if it occurred, would demonstrate the resilience of the funerary cult and its capacity to adapt to circumstances that its founders had not anticipated. The artistic discoveries at Meidum also raise questions about the relationship between artistic production and architectural construction in the early 4th Dynasty. Questions about whether the artists and the builders were part of the same institutional framework, whether they shared the same training and the same professional structures, and whether the artistic quality of the tomb decorations was related to the engineering quality of the pyramid itself. The questions are difficult to answer. The evidence for the institutional organization of artistic production in the early 4th dynasty is limited, but the co-occurrence of high-quality art and ambitious, if flawed, architecture at Meidum suggests that the site was a center of creative activity in multiple domains, a place where the best artists and the most ambitious builders of the early 4th dynasty came together in the service of the pharaoh and his court. The role of the Meidum site in the broader geography of Old Kingdom pyramid construction. The spatial distribution of pyramid sites along the western edge of the Nile Valley from Abu Roash in the north to Meidum in the south provides additional context for understanding the decisions that shaped the pyramid building program. The Meidum site is the southernmost major pyramid site of the Old Kingdom, located far from the capital at Memphis and from the established cemetery at Saqqara, where the Step Pyramid and the other 3rd dynasty tombs were built. The distance from the capital may have contributed to the decision to abandon the site after the collapse. The remote location made the Meidum site less convenient and less efficient than the sites closer to Memphis that Sneferu would choose for his subsequent pyramids at Dashur. The decision to move the building program from Meidum to Dashur, a decision that was almost certainly influenced by the Meidum collapse, had significant consequences for the development of the pyramid building tradition. The Dashur site was closer to Memphis, reducing the logistical challenges of transporting workers and materials. The Dashur site had better quality limestone, harder and more suitable for the structural demands of true pyramid construction, and the Dashur site was on the established route between Memphis and the southern provinces, making it more accessible to the administrative and supply networks that the construction required. The move to Dashur was a strategic decision, a decision that reflected the lessons of the Meidum experience and that positioned the building program for the subsequent successes at the Bent Pyramid and the Red Pyramid. the artistic legacy of the Meidum site, the paintings, the sculptures, and the decorative arts that were produced by the artists who worked at the site has proven more durable than the architectural legacy. The Meidum geese are today one of the most recognized images in the history of Egyptian art, reproduced in textbooks, displayed in museums, and admired by millions of people who may never have heard of the Meidum Pyramid or the collapse that defines its history. The statues of Rahotep and Nofret are similarly serrated. Their lifelike eyes and their natural poses make them among the most accessible and the most appealing of all Egyptian sculptures, works that bridge the gap of 4,600 years and that speak directly to the modern viewer with an immediacy that few ancient artworks can match. The development of Egyptian funerary architecture, from the simple arrangement at Meidum to the elaborate complexes at Giza, reveals progressive elaboration mirroring the refinement of the pyramid form. The Meidum complex was simple: a pyramid, a small mortuary temple, a causeway, and a valley temple. The Giza complexes were vast assemblages of temples, causeways, boat pits, subsidiary pyramids, and courtiers' tombs, providing comprehensive ritual infrastructure. The elaboration reflected deepening understanding of ritual requirements and growing ambition to provide more effective spiritual sustenance. The simple offering at Meidum, a table and 2 stelae, was adequate for basic ritual. The elaborate mortuary temples at Giza supported complex programs, including daily offerings, festival celebrations, and seasonal ceremonies. The question of what happened to the Meidum site after the collapse is addressed only partially by the evidence. The mastaba tombs continued to be used into the later Old Kingdom, suggesting the site retained religious significance. The mortuary temple may have continued functioning, and the funerary cult may have adapted to the damaged pyramid. The continued use would demonstrate the resilience of the cult and its capacity to adapt to unanticipated circumstances. The Meidum site has also yielded evidence for the development of Egyptian construction techniques through the analysis of the tools and the working methods that the builders employed. The quarry marks on the remaining core blocks, the chisel marks, the wedge holes, and the channel cuts that show how the blocks were extracted from the bedrock are consistent with the standard Old Kingdom quarrying techniques, but show some variations that may reflect the specific characteristics of the Meidum limestone and the specific requirements of the Meidum construction. The careful study of these tool marks has provided valuable information about the efficiency and the productivity of the quarrying operations, information that usefully supplements the data from other pyramid sites and that contributes to our overall understanding of the industrial processes that sustain the pyramid building program. The comparison between the Meidum construction techniques and the techniques used at subsequent pyramid sites reveals a pattern of progressive improvement. Improvements in the precision of the block cutting, in the quality of the surface finishing, in the tightness of the joints, and in the overall efficiency of the construction process. The improvements were incremental. Each generation of builders produced work that was slightly better than the work of the previous generation, but the cumulative effect was dramatic, transforming the rough, somewhat irregular masonry of the early pyramid tradition into the precise, tightly fitted, geometrically accurate masonry of the Great Pyramid. The Meidum construction techniques were the baseline, the starting point against which the subsequent improvements can be measured, and from which the trajectory of the tradition's development can be traced. The Meidum Pyramid's relationship to the development of Egyptian mathematical knowledge is another aspect of its significance that extends beyond the specific context of pyramid construction. The construction of pyramids required the application of mathematical principles of geometry, trigonometry, and measurement that were essential for the surveying, the layout, and the alignment of the structures. The mathematical knowledge that the builders possessed was practical rather than theoretical. It was expressed in terms of specific procedures and specific ratios, rather than in terms of abstract theorems and formal proofs. But the knowledge was real. It was sufficient for the construction of structures of extraordinary scale and precision, and it was transmitted across generations through the apprenticeship system and the scribal schools that trained the administrators and the surveyors who managed the construction projects. The specific mathematical concept that was most directly relevant to pyramid construction was the sect, the ancient Egyptian measure of slope that expressed the horizontal displacement of a surface for a given vertical rise. The sect was the practical equivalent of the modern concept of the cotangent of the slope angle. It provided a way of specifying and measuring the angle of a pyramid's face that was directly applicable to the construction process. The builders used the sect to control the angle of each course as it was laid, checking the slope with measuring instruments and adjusting the position of the blocks to ensure that the angle was maintained consistently from base to apex. The sect concept was already in use at the time of the Meidum construction. It was part of the mathematical toolkit that the builders had inherited from the preceding generations of stone construction. The application of the sect at Meidum, the specification of the angle, the control of the slope during construction, and the verification of the finished surface was standard practice that the builders executed with the competence that their training and their experience had provided. The collapse was not caused by a failure of mathematics. The angle was specified correctly, and the slope was maintained accurately. The collapse was caused by a failure of structural engineering, the failure to recognize that the forces created by a structure of this size and this angle exceeded the capacity of the friction-dependent casing to resist them. The broader significance of the Meidum site for the study of ancient Egyptian society extends beyond the pyramid and the mastaba tombs to encompass the entire community of people who lived, worked, and died in the vicinity of the construction site. The Meidum community was a microcosm of the Old Kingdom state, a gathering of individuals from every level of the social hierarchy, from the pharaoh at the top to the laborers at the bottom, all brought together by the construction project and all contributing, in their different ways, to the enterprise of building a monument for the pharaoh's eternal survival. The community included skilled craftsmen, quarrymen, masons, sculptors, and painters who produced the physical fabric of the pyramid and the tombs. The community included administrators, scribes, overseers, and officials who managed the logistics and the finances of the construction. The community included priests, religious specialists who performed the rituals and the ceremonies that accompanied the construction and that would sustain the pharaoh's spirit after his death. And the community included laborers, the corvée workers who provided the muscle power that the quarrying, the transport, and the construction required. The considerable diversity of the Meidum community is clearly reflected in the diversity of the tombs that surround the pyramid. Tombs that range from the large and elaborately decorated mastabas of the senior officials to the simple pit burials of the laborers, each one faithfully reflecting the social status and the economic resources of its occupant. The diversity of the tombs provides evidence for the social stratification of the Old Kingdom state. The strict hierarchical ranking of individuals according to their birth, their office, and their relationship to the pharaoh that determined their access to resources and their prospects for the afterlife. The irony is that the artistic treasures of Meidum have survived while the architectural monument has not. The paintings and the sculptures, produced by the same culture and the same court that built the pyramid, have outlasted the structure that was designed to endure for eternity, while they were designed merely to decorate the tombs of the courtiers. The irony illustrates a broader truth about the durability of human achievements. The truth that the things we expect to last are not always the things that do, and that the things we create without expectations of permanence sometimes prove more durable than the things we build with permanence as their explicit purpose. The sixth exploration examines the Meidum Pyramid's place in the broader sequence of Egyptian pyramid development, its role as the first failed experiment in a series of experiments that would eventually produce the true pyramid form. The Meidum Pyramid is the first chapter in the story of the true pyramid, the chapter in which the ambition to build a smooth-sided structure first encounters the reality of what that ambition requires. The chapter is a tragedy, a story of ambitious plans defeated by inadequate knowledge, of a structure that was conceived in hope and ended in ruin. But the tragedy is productive. It produces the knowledge that the subsequent chapters will apply, the lessons that the bent pyramid and the red pyramid will incorporate, and the understanding that the Great Pyramid will perfect. Step back now from the engineering details and the archaeological debates and the scholarly hypotheses. Step back from the Meidum Pyramid as a construction project and look at it as something larger, as a monument to the beginning of a process, the painful first step on a journey that would transform the built environment of the ancient world. The Meidum collapse was the beginning of the journey that led to the Great Pyramid of Giza. The statement sounds paradoxical. How can a collapse be the beginning of a journey toward the greatest construction achievement of the ancient world? The answer is that the collapse generated the knowledge that the journey required. The knowledge of what went wrong, the knowledge of why it went wrong, and the knowledge of what would need to be different if the next attempt were to succeed. The collapse was not the end of the story. It was the beginning, the painful, destructive, necessary beginning of a process of learning that would extend over decades and that would produce, through the accumulation of hard-won insights, the engineering knowledge that built the Great Pyramid. Let that sink in. The Meidum Pyramid raises profound questions about the nature of ambition, whether the desire to achieve something unprecedented is a virtue or a liability, whether the willingness to take risks is strength or foolhardiness. The questions are embodied in the physical reality of the collapsed pyramid, the tower that stands, and the rubble that surrounds it. The ambition was real and legitimate, motivated by genuine religious beliefs, supported by genuine resources, executed by genuine professionals. The ambition was not reckless. It was the considered judgment of experienced builders who believed the conversion was feasible. The ambition was also fundamentally wrong, based on incomplete understanding of the forces the true pyramid form would create. The builders did not and could not know what they did not know. The revelation of what they did not know was the most valuable thing that happened at Meidum. More valuable than the pyramid itself or the labor invested. The revelation was the beginning of knowledge, the beginning of understanding that would produce the Great Pyramid and sustain the Egyptian building program for 2,000 years. The revelation was undeniably painful and enormously costly, in every material sense a disaster. But it was also productive. The Meidum collapse also teaches about the relationship between confidence and knowledge, the danger of proceeding with confidence not supported by adequate understanding. The builders were confident, based on real experience and skill, but the confidence was misplaced. The true pyramid conversion was fundamentally different from the step pyramid construction they had mastered. The failure to recognize the difference was the root cause of the collapse. The critically important lesson about misplaced confidence has direct and practical implications for modern engineering practice, reflected in the emphasis on risk assessment, peer review, testing, and systematic identification of failure modes. These carefully designed procedures are intended to prevent the kind of confidence-driven failure, ensuring that engineers' confidence is always and thoroughly supported by adequate analysis reviewed by independent experts. The deeply important question of what the collapse meant for the pharaoh, whether Huni or Sneferu, connects the engineering story to personal and political dimensions. The pharaoh's tomb was his most important possession, the instrument of his transformation from mortal king to immortal god. Its destruction was a catastrophe of the first order affecting prestige, legitimacy, and eternal prospects that would have reverberated powerfully through the court and the entire kingdom. The relationship between physical structures and the knowledge systems that produce them is relevant to every civilization. The Meidum Pyramid was designed to endure for eternity. The knowledge that produced it was held in human minds, transmitted through apprenticeship, and vulnerable to institutional change. The structure and the knowledge had different durabilities, and the collapse illustrates both the vulnerability of insufficient knowledge and the generative power of failure to produce new knowledge. The collapse generated specific, concrete, practical, experientially validated knowledge about the forces acting on a pyramidal casing and the conditions under which those forces cause failure. This knowledge was new. It had not existed before the collapse. It was valuable, immediately applicable, and the foundation of all subsequent true pyramid construction. The relationship between physical failure and knowledge generation is one of the fundamental dynamics of human civilization, as relevant today as 4,600 years ago. The Meidum Pyramid's influence on the modern popular understanding of ancient Egypt, on the image that the general public holds of the Egyptian pyramid building tradition, is less than it should be, given the pyramid's importance to the tradition's development. The popular image of the pyramids is dominated by the Great Pyramid and the Sphinx at Giza, monuments that are iconic, instantly recognizable, and universally associated with ancient Egypt. The Meidum Pyramid is absent from this popular image. It is not included in the standard tourist itinerary. It is not featured in most documentary films about ancient Egypt, and it is not reproduced on the postcards and the souvenirs that constitute the visual vocabulary of popular Egyptology. The absence of the Meidum Pyramid from the popular image is a distortion, because the popular image without Meidum presents the pyramid-building tradition as a story of unbroken success, a progression from the step pyramid to the Great Pyramid that proceeds smoothly and inevitably from one achievement to the next. The Meidum collapse disrupts this narrative. It introduces failure, crisis, and destruction into a story that the popular imagination prefers to tell as a triumph. The disruption is essential because the narrative without the disruption is false. The pyramid-building tradition was not a story of unbroken success. It was a story of failures and recoveries, of problems and solutions, of ambitions that outpaced knowledge and knowledge that eventually caught up. The Meidum collapse is the chapter of the story that makes the rest of the story true. The chapter that provides the context of failure against which the subsequent successes can be properly understood and appreciated. The absence of the Meidum Pyramid from the popular image of ancient Egypt is a distortion, because the popular image without Meidum presents the pyramid-building tradition as unbroken success, a smooth progression from step pyramid to Great Pyramid. The Meidum collapse disrupts this narrative, introducing failure, crisis, and destruction into a story the popular imagination prefers to tell as triumph. The disruption is essential because the narrative without it is false. The tradition was not unbroken success, but failures and recoveries, problems and solutions, ambitions that outpaced knowledge and knowledge that eventually caught up. The Meidum collapse is the chapter that makes the rest of the story true, providing the context of failure against which subsequent successes can be properly understood and appreciated. The correction of the popular narrative is one of the most important contributions that the study of the Meidum Pyramid can make to public understanding of ancient Egypt, replacing the fiction of smooth progress with the truth of productive failure. The Meidum Pyramid embodies this dynamic more visibly than any other ancient structure, a collapsed building standing as permanent evidence of a failure that was also a beginning, a destruction that was also a creation, and a loss that was also the most valuable gain the Egyptian building tradition ever received. The Meidum collapse teaches a lesson about the nature of innovation that is relevant far beyond the history of architecture. The lesson is this: the first attempt at something fundamentally new will almost always fail, not because the people who make the attempt are incompetent, not because the attempt is poorly planned or poorly executed, but because the knowledge needed to succeed at something fundamentally new can only be gained through the attempt itself, through the experience of doing the thing, of encountering the problems that the thing creates, and of discovering, through painful observation, the solutions that the problems require. The knowledge is experiential. It cannot be acquired in advance, it cannot be deduced from theory, and it cannot be inherited from previous work on different problems. The knowledge can only be gained by doing, and the doing will, almost inevitably, produce a failure that is the source of the knowledge. The Meidum builders were not failures. They were pioneers, the first people in human history to attempt the construction of a true pyramid, the first to confront the engineering challenges that the form presented, and the first to discover, through the destruction of their work, the specific knowledge that would be needed to make the form succeed. The pioneering was painful. It cost years of labor, millions of blocks of stone, and the hopes of a pharaoh who expected his tomb to stand for eternity. But the pioneering was essential. Without it, the knowledge would not have been generated, the lessons would not have been learned, and the subsequent achievements would not have been possible. This is not science fiction. This is the actual history of one of the greatest engineering traditions in human civilization, a tradition that began with a catastrophic failure and that transformed the failure through decades of disciplined learning into the most impressive construction achievement of the ancient world. Let that sink in. The Meidum Pyramid's relationship to the broader arc of Egyptian civilization, not merely to the pyramid building tradition, but to the cultural, artistic, and intellectual life of the Old Kingdom, is an aspect of the site's significance that deserves emphasis. The Meidum site was not merely a construction project, it was a cultural center, a community of artists, craftsmen, priests, and administrators who produced some of the finest works of art in the entire history of Egyptian civilization. The Meidum geese, the statues of Rahotep and Nofret, the painted scenes in the mastaba of Nefermart. These works demonstrate that the early 4th dynasty was a period of extraordinary artistic vitality, a period in which the technical skills of the artists and the aesthetic sensibility of the patrons combined to produce works of lasting beauty and enduring influence. The artistic achievements at Meidum are all the more remarkable because they occurred during a period of architectural failure, the period in which the pyramid's casing collapsed and the ambition to build a true pyramid was destroyed. The juxtaposition of artistic success and architectural failure is one of the most interesting features of the Meidum story. It demonstrates that the creative energies of a civilization are not confined to a single domain, that excellence in one field does not prevent failure in another, and that the artistic vitality of a culture can coexist with the engineering limitations that prevent it from achieving its architectural ambitions. The Meidum geese, discovered by Auguste Mariette in the mastaba of Nefermart in 1871, are one of the masterpieces of ancient Egyptian painting. The painting depicts 6 geese, 3 facing left and 3 facing right, rendered with a naturalism and a precision that is extraordinary for any period of ancient art. The feathers are painted with minute attention to detail, each feather individually rendered, with variations in color and texture that capture the specific characteristics of the species depicted. The geese are set against a plain background, a compositional choice that focuses the viewer's attention on the birds themselves, and that creates a sense of clarity and simplicity that is characteristic of the finest Egyptian art. The painting has been dated to the early 4th dynasty, making it contemporary with the pyramid's construction and providing evidence for the artistic culture that flourished at Meidum during the period of the pyramid building program. The Meidum collapse also teaches a lesson about the relationship between confidence and knowledge, about the danger of proceeding with confidence that is not supported by adequate understanding. The builders of the Meidum conversion were confident. They believed, on the basis of their existing experience, that the conversion was feasible, and that the techniques they planned to use were adequate for the task. The confidence was not irrational. It was based on real experience and real skill, on decades of successful construction projects that had validated the builder's capabilities. But the confidence was misplaced, because the specific task of converting a step pyramid to a true pyramid was fundamentally different from the tasks that the builder's experience had prepared them for, and the techniques that had worked for those earlier tasks were not adequate for this new and unprecedented challenge. The misplacement of confidence is one of the most common causes of engineering failure. In the ancient world and in the modern world alike, engineers who have succeeded at many previous projects develop a confidence in their methods and their understanding that is generally justified, but that can become dangerous when it is extended to new and unprecedented challenges. The confidence can blind the engineers to the differences between the new challenge and the previous ones, differences that may be subtle, but that can have catastrophic consequences if they are not recognized and addressed. The Meidum builders were blinded by their confidence. They did not recognize that the true pyramid conversion was fundamentally different from the step pyramid construction they had mastered, and the critical failure to recognize this fundamental difference was the root cause of the collapse. The critically important lesson about misplaced confidence has direct and practical implications for modern engineering practice. Implications that are reflected in the modern engineering profession's emphasis on risk assessment, on peer review, on testing, and on the systematic identification and evaluation of potential failure modes before construction begins. The modern procedures are designed to prevent the kind of confidence-driven failure that destroyed the Meidum casing. They are designed to ensure that the engineer's confidence is supported by adequate analysis, that the analysis is reviewed by independent experts, and that the potential failure modes are identified and addressed before they can produce a catastrophe. The procedures are not perfect. Modern engineering failures still occur, but they are effective, and their effectiveness is demonstrated by the rarity of catastrophic failures in modern engineering practice compared to the frequency of such failures in the ancient world. The question of what the Meidum collapse meant for the pharaoh who commissioned it, whether Huni or Sneferu, is a question that connects the engineering story to the personal and political dimensions of the pyramid building program. The collapse was not merely an engineering failure, it was a political failure, a religious failure, and a personal failure that affected the pharaoh's reputation, his legitimacy, and his prospects for eternal survival. The pharaoh's tomb was his most important possession, the structure that would house his body for eternity, and that would serve as the instrument of his transformation from mortal king to immortal god. The destruction of the tomb, or even the partial destruction of its outer surface, was a catastrophe of the first order, a blow to the pharaoh's prestige and his prospects that would have reverberated powerfully through the court and the entire kingdom. The question of what would have happened if the Meidum collapse had not occurred, if the casing had held, if the conversion had succeeded, and if the Meidum pyramid had become the first true pyramid in history, is a counterfactual question that illuminates the significance of the collapse by imagining its absence. If the conversion had succeeded, the builders would have had no reason to develop the countermeasures that the collapse forced them to adopt. No reason to change the orientation of the casing courses from slope parallel to horizontal. No reason to improve the bonding between the casing and the core. No reason to reassess the relationship between the angle of the pyramid and the forces that the angle created. The builders would have continued with the techniques that had produced the successful conversion. Techniques that were, as the collapse demonstrated, fundamentally inadequate for the construction of true pyramids at the scales that subsequent pharaohs would demand. The success of the Meidum conversion would have been, paradoxically, a disaster for the pyramid building tradition, because it would have validated a set of techniques that were insufficient for the task, creating a false confidence that would have led to larger and more catastrophic failures when the techniques were scaled up to the dimensions of the Great Pyramid. The Meidum collapse prevented this false confidence. It demonstrated, in the most dramatic possible way, that the existing techniques were not adequate, and it forced the builders to develop new techniques that were. The collapse was, in this sense, a gift, a painful, destructive, expensive gift that the tradition needed in order to progress beyond the limitations of its existing methods. The Meidum Pyramid also teaches a lesson about the relationship between innovation and risk, about the fact that every attempt to do something new involves the possibility of failure, and that the possibility cannot be eliminated in advance, only managed after the fact. The builders of the Meidum Pyramid took a risk. The risk of attempting something that had never been done before, the risk of converting a step pyramid to a true pyramid using techniques that had not been tested at this scale. The risk produced a failure, but the failure produced knowledge, and the knowledge produced success. The sequence, risk, failure, knowledge, success, is the fundamental sequence of engineering progress, and the Meidum Pyramid is its earliest and most visible example in the history of monumental architecture. The philosophical question that the Meidum collapse raises, the question of whether failure is a necessary precondition for progress, whether the knowledge needed for success can only be gained through the experience of failure, is a question that has been debated by philosophers, historians, and engineers for centuries. The question does not have a simple answer. Not all failures lead to progress, and not all progress is preceded by failure. But the Meidum case provides strong evidence for the proposition that, in the specific context of engineering innovation, failure is one of the most productive sources of knowledge, because the failure reveals the limits of existing understanding in a way that no amount of theoretical analysis can match, and because the knowledge of those limits is precisely the knowledge that is needed to extend them. The Meidum collapse revealed the specific limits of the builders' understanding, the limits of their knowledge about bonding, about bedding plane orientation, about force distribution, about the structural behavior of large masonry assemblies under gravitational loading. The revelation was painful. It cost the builders their building, their investment, and their confidence. But the revelation was also productive. It generated the specific knowledge that the builders needed to extend their capabilities beyond the limits that the collapse had revealed, and it set in motion the process of learning and refinement that would eventually produce the Great Pyramid. The Meidum collapse did not cause progress. It caused knowledge, and the knowledge caused progress. The distinction is important because it highlights the role of the human response to failure, the active process of analysis, learning, and application that transforms a destructive event into a productive one. The grief moment of the Meidum story is the collapse itself. Not because the collapse destroyed a building, but because the collapse destroyed a hope. The builders had hoped to create something new, a smooth-sided pyramid, a form that had never existed before, a monument that would surpass anything that the previous generation had achieved. The hope was legitimate. It was based on real ambition, real skill, and real resources. And the hope was destroyed, not by an enemy, not by a natural disaster, but by the gap between what the builders knew and what they needed to know, the gap between their experience and their ambition, the gap that could only be closed by the knowledge that the collapse itself would generate. The destruction of hope is the most painful form of loss, more painful than the destruction of property, more painful than the loss of time and labor, more painful even than the loss of the building itself. The builders of Meidum lost their hope, the hope that the true pyramid was within their reach, the hope that their knowledge was sufficient for the task, the hope that the ambition they had invested in the project would be rewarded with success. The loss was devastating, but it was also, in retrospect, the most valuable thing that happened to the Egyptian building tradition, because the loss of the hope forced the builders to confront their own ignorance, to recognize the limits of their knowledge, and to begin the painful process of acquiring the knowledge that their ignorance had cost them. The Meidum Pyramid stands in the desert today, a lonely tower surrounded by rubble, a shape that does not match any category of Egyptian architecture, a structure that is neither a step pyramid nor a true pyramid, but something else entirely, something that exists only because a plan went wrong and the wreckage was left standing. The shape is unique. There is nothing else like it in Egypt, nothing else like it in the world. The uniqueness is the product of failure, the failure that stripped the casing from the core and left the core standing alone, exposed and diminished, a monument to the most spectacular structural collapse in the history of the ancient world. The implications of the Meidum collapse extend far beyond the history of Egyptian architecture. They extend to the broadest questions about human progress, about how civilizations learn, how knowledge accumulates, and how the achievements of one generation build on the failures of the previous one. The Meidum collapse is a universal story, a story about what happens when ambition outpaces knowledge, when the desire to achieve something new confronts the reality that the knowledge needed for the achievement does not yet exist, and when the confrontation produces a failure that is both destructive and instructive. The modern world faces its own versions of the Meidum collapse, its own instances of ambition outpacing knowledge, of projects that fail because the engineering challenges are more demanding than anticipated, of technologies that produce unexpected consequences because the understanding of the technology is incomplete. The parallels are direct. The Meidum collapse is, in structural terms, the same kind of event as a modern bridge failure, a dam collapse, or a building structural failure. The ancient event and the modern events share the same root cause, the gap between what the builders know and what they need to know, and they share the same lesson, that the gap can only be closed through the painful process of learning from the failure itself. The Meidum Pyramid is also a monument to the courage of the builders who came after. The builders of the Bent Pyramid and the Red Pyramid, who knew what had happened at Meidum, and who nevertheless attempted, for a second and a third time, to build a true pyramid. The courage is extraordinary, because the builders knew the risks, they had seen the consequences of failure, and they chose to proceed anyway, accepting the possibility that their attempt might also fail, and that their work might also end in rubble. The courage was rewarded. The Bent Pyramid was completed in compromised form. The Red Pyramid was completed successfully. And the Great Pyramid was built on the foundation of the knowledge that all three earlier attempts had generated. But the courage was real, and it deserves to be recognized as one of the essential elements of the story, an element without which the subsequent achievements would not have been possible. The Meidum Pyramid's place in the modern archaeological landscape is one of quiet significance, a site that is less visited, less studied, and less celebrated than the more famous pyramids of Giza and Dashur. But that holds a unique and irreplaceable position in the story of Egyptian architecture. The site is relatively remote, located roughly 100 kilometers south of Cairo, off the main tourist routes, and accessible only by a journey that takes visitors away from the familiar monuments of the Nile Valley into the desert landscape of the Fayum. The remoteness has protected the site from the commercialization that has transformed Giza, but it has also limited the public's awareness of the site and its significance. The conservation of the Meidum Pyramid presents unique challenges that are different from the conservation challenges at other pyramid sites, because the Meidum Pyramid's collapse has created a structural situation that has no parallel elsewhere in Egypt. The core that remains standing is a steep-sided tower of rough limestone, a structure that is subject to the same forces of erosion, thermal cycling, and gravitational loading that affect all stone structures in the Egyptian desert, but that is also subject to the specific stresses created by its unusual shape and its exposed surfaces. The rubble apron that surrounds the core is also subject to erosion. The blocks and fragments are gradually being worn away by wind and sand, and the rubble field is slowly being covered by the desert sand that accumulates around and over the debris. The scholarly study of the Meidum Pyramid continues to produce new insights, as new analytical techniques are applied to the physical evidence, and as new theoretical frameworks are developed for understanding the engineering and the architectural history of the site. Recent studies have used ground-penetrating radar, thermal imaging, and photogrammetric surveying to investigate features of the pyramid that were not accessible to earlier generations of scholars. Features such as the internal structure of the rubble apron, the condition of the unexposed surfaces of the core, and the distribution of voids and passages within the body of the pyramid. The studies have confirmed the general picture that Petrie and his successors established. The picture of a step pyramid that was converted to a true pyramid, and that collapsed when the conversion casing failed, but they have also added new details and new nuances that enrich our understanding of the site and its significance. The relationship between the Meidum Pyramid and the development of Egyptian civil engineering, the broader tradition of stone construction that encompassed not only pyramids but temples, fortifications, causeways, and other monumental structures, is an aspect of the site's significance that extends beyond the narrow focus on pyramid construction. The lessons of the Meidum collapse were not confined to pyramid building. They were applicable to any large-scale stone construction project that involved the assembly of heavy blocks on sloping surfaces, and the knowledge that the collapse generated was incorporated into the broader tradition of Egyptian engineering that governed all categories of monumental construction. The role of Flinders Petrie in the modern understanding of the Meidum pyramid deserves extended discussion, because Petrie's work at the site established the framework of knowledge that all subsequent studies have built upon. Petrie arrived at Meidum in 1891, one of the first stops in a career that would make him the most influential Egyptologist of his generation, and one of the founders of modern archaeological method. Petrie's approach to the Meidum pyramid was characteristic of his broader approach to archaeology: meticulous, systematic, and driven by the conviction that the physical evidence, carefully recorded and rigorously analysed, could reveal truths about the ancient world that no written text could provide. Petrie measured the pyramid with a precision that was remarkable for the period, using surveying instruments and mathematical techniques that allowed him to determine the dimensions of the structure with an accuracy that subsequent surveys have confirmed. He mapped the rubble apron, recording the extent of the debris field, the size distribution of the blocks, and the composition of the rubble with a thoroughness that provided the foundation for all subsequent analyses of the collapse. He explored the internal passages and chambers, recording their dimensions, their orientations, and their condition with the same precision that he brought to the external survey, and he published his findings in a detailed report that has become one of the classic texts of Egyptian archaeology, a model of rigorous, evidence-based scholarship that established standards that the discipline continues to follow. Petrie's analysis of the Meidum pyramid was not merely descriptive, it was interpretive. He attempted to reconstruct the sequence of construction phases that the pyramid had undergone, from the initial 7-step phase to the 8-step expansion to the final true pyramid conversion, and he proposed an explanation for the collapse that emphasized the inadequacy of the bonding between the casing and the core. His interpretation was not universally accepted. Subsequent scholars have proposed alternative explanations and have challenged some of his specific conclusions, but his interpretive framework has proven remarkably durable, and the basic picture that he established of a step pyramid converted to a true pyramid and destroyed by the failure of the conversion casing remains the standard interpretation of the site. The visitor who comes to Meidum today encounters a landscape that is at once desolate and powerful, a flat desert plain stretching to the horizon, broken only by the stark vertical profile of the pyramid's remaining core and by the gentle slope of the rubble apron that extends outward from the base. The landscape is empty. There are no other monuments nearby, no other structures visible, no other signs of human habitation or activity for kilometers in every direction. The emptiness is appropriate. It creates a sense of isolation that matches the isolation of the pyramid itself, a structure that has been standing alone in the desert for more than 4,600 years, stripped of its companions and its context, reduced to its essential core by the forces that destroyed everything around it. The experience of visiting Meidum is different from the experience of visiting any other pyramid site in Egypt. At Giza, the visitor is surrounded by monuments: the 3 great pyramids, the Sphinx, the temples, the causeways, the tombs of the courtiers, and the officials who served the pharaohs. At Darsha, the visitor can see both the bent pyramid and the red pyramid, and the contrast between the two tells the story of the tradition's development. At Meidum, the visitor sees only the tower, a solitary structure rising from the rubble, stripped of its outer layers, its original form visible only in the imagination. The solitude of the tower is part of its power. It forces the visitor to confront the structure on its own terms, without the distractions and the comparisons that the more crowded sites provide. The descent into the Meidum pyramid's interior, through the narrow entrance passage on the north face, down the sloping corridor, and into the burial chamber with its corbelled ceiling is an experience that connects the modern visitor to the ancient builders in a direct and physical way. The passage is narrow and steep. The visitor must stoop to avoid the low ceiling, and the descent creates a sense of confinement that intensifies as the passage leads deeper into the body of the pyramid. The burial chamber, when it is reached, opens up, the corbelled ceiling soaring above the visitor's head, the limestone walls, smooth and precisely fitted, the space surprisingly large after the confinement of the passage. The chamber is empty. No mummy, no sarcophagus, no grave goods remain, but the space is impressive, a testament to the builder's skill in creating internal spaces that were structurally sound and aesthetically compelling. The Meidum Pyramid reminds us that the history of engineering is not a history of unbroken success. It is a history of failures and recoveries, of problems and solutions, of ambitions that outpace knowledge and knowledge that eventually catches up. The reminder is valuable because the modern tendency to celebrate success and to forget failure creates a distorted picture of how engineering progress actually occurs and obscures the essential role that failure plays in the generation of new knowledge. The Meidum Pyramid corrects this distortion. It places failure at the center of the story, where it belongs, and it demonstrates that the most productive failures are not the ones that are quickly forgotten, but the ones that are carefully studied, thoroughly analyzed, and systematically incorporated into the practices and the procedures that govern subsequent work. The relationship between the Meidum collapse and the subsequent development of the pyramid building tradition is a relationship of cause and effect. The collapse caused the knowledge, and the knowledge caused the subsequent achievements. The relationship is direct. Each subsequent pyramid can be understood as a response to the Meidum collapse, an attempt to avoid the specific failure modes that the collapse had revealed, while pushing closer to the goal of a structurally sound true pyramid. The bent pyramid was a response. Its improved bonding between casing and core was a direct application of the Meidum lesson. The red pyramid was a response. Its horizontal courses and its conservative angle were the mature application of the lessons that Meidum and the bent pyramid had taught. The Great Pyramid was the culmination, the final expression of the knowledge that had been accumulating since the rubble first cascaded down the sides of the Meidum Pyramid and spread across the desert floor. The Pyramid of Meidum stands alone in the desert, more alone than any other pyramid in Egypt, more isolated, more forgotten, more remote from the tourist routes and the popular imagination than the famous monuments of Giza or the dramatic structures of Darsha. The isolation is fitting, because the Meidum Pyramid is a structure that belongs to the beginning, and beginnings are always lonely. The beginning of any great endeavor is the moment of maximum uncertainty, maximum risk, and maximum vulnerability. The moment when the outcome is unknown, the path is untested, and the possibility of failure is highest. The Meidum Pyramid embodies this moment, the moment when the Egyptian builders first attempted the true